Well, welcome back. I'm so sorry. I had a technology disruption. I'm in the middle of the 6.4 notes. So we're going to just do a part 2 video, picking right up where we left off. So where we were last on, we were having you guys were using the folder 3 from the exploration on Desmos to explore and then sketch these graphs. And so we had some kind of interesting things. The first two questions, under question 3, the first two graphs ended up being shaped at what we would call a cardioid. So it kind of looks circular on one side and then has this heart shape, kind of like a dip right in here. And that goes right to the origin. That's called a cardioid. And you might want to notice that these numbers are the same when you have a cardioid. The next one's also a cardioid. It's just a cardioid that goes along the negative side of the x-axis, but again, has that heart shape dip right at the origin. Now, unlike a normal heart, there is not a point or anything. This is rounded here on the end. Also notice that these numbers are the same. For a cardioid, that would always be true. This next one over here still has a little bit of that kind of heart shape, but it doesn't go to the origin. And so, in fact, I think when you graph it on Desmos, it's pretty flat, actually, right there. It doesn't have much of a little dip. There's just the tiniest little one. This is called a limmason with dimple. A limmason with dimple. The snail-shaped graph. Limmason means snail-shaped. And it has this little kind of mild indentation here. And that indentation can sometimes be pretty flattened out depending on the numbers that you end up with. But notice that this time those numbers are different than each other. And in fact, the first number, that 4, is larger than the multiplier of cosine, the 3. This next one is called a limmason with an inner loop. Limmason. There's actually like a little mark underneath limmason. That's C. I don't know how to write it. I apologize. I do not speak French quite clearly. And this one has an inner loop. So again, it kind of is that snail shape, but it has this inner loop with this portion right in here that it kind of backtracks onto itself and forms this extra little loop. These numbers will be different when you have an inner loop. It's not the minus that makes the inner loop. What makes the inner loop is the fact that this number is larger than what's being added or subtracted on. And we'll see this as we explore these a bit more. When you have a cardioid, the numbers in the front, we'll call those numbers in the front A and B, they are going to be the same. And please notice that the cardioid always goes through the origin for that like indentation of the heart. A limmason with dimple. This number right here, A, is going to be larger than B. Now, they can have various signs, but the absolute value, their magnitude, would be larger than B. And so what that would look like is, and just kind of a note, this one would never go through the origin. We'll see why when we explore this a bit more. These will never go through the origin. The limmason with an inner loop, this one right here, we would, wow, written backwards. Let's fix this. This A is smaller than B. A is smaller than B. I apologize. We've had 2 typos on this notes. So A is smaller than B. And that's actually how we're going to backtrack and get the inner loop. We'll see it when we do plug in some values. Now this one with the inner loop, it will still go through the origin before forming the inner loop. And all of them have kind of this circular-ish shape, snail shape. But there's a couple interesting things about them. Now, you can certainly memorize what we just talked about here. And then we're also going to have some ways on how to do these with a table of value, which is actually requires much less memory space and I think is super straightforward and easy and will be helping a lot. I'm going to pause the video. Hopefully I won't turn it off this time. And I want you to go back, and this time you're going to turn on graph 11, which is the graph of our sine theta. So you'll turn off, or I guess it's graph 12. So you'll turn off 10, turn that one off. turn on graph 12. You're going to use the sliders for A and B to explore and see what happens. Pay close attention. When is it a cardioid? When are A and B cardioids? When do we have an inner loop? When do we have a limosome with dimple? And then also, when are we on the positive side of the y-axis? And maybe when are we on the negative side of the y-axis? How does that happen? When does that happen? So we will restart the video after you've had a chance to explore. You're also going to use Desmos to change the sliders to sketch these 3 graphs. And then unpause the video and we'll come back together. All right, so the first one, we have a cardioid. Notice how A and B are the same values. And because this is a sine function, notice the symmetry along the y-axis. Well, supposed symmetry, if I drew it better, perhaps. This second one is a limosome with dimple. Limosome, oh, not with a dimple, with an inner loop, my apologies. That will happen when the value of B is larger than the value of A. They can have various signs. Notice how this one also has symmetry along the y-axis, supposedly, if I draw it well. And also notice that both the cardioid and the limosome with inner loop will pass through the origin of the graph. The last one is a limosome with dimple. And a limosome with dimple will not pass through the origin. Notice how it will miss that origin in there. And also notice the symmetry along the y-axis, or at least supposed symmetry. So the table on the next page gives us some summary information. So cardioids, what do they look like? Now, all of these would be limosomes. A cardioid is a special category of limosome. And so they all have A plus or minus B cosine theta, or that could be with sine. But if A and B are the same numbers, we'll have a cardioid. The dimple is right at the heart of the origin. The dimple of the heart's right at the origin. Cosine would have symmetry around the x-axis. This one's sine, so it'll have symmetry along the y-axis. And you could just plot some points. I usually plot these angles right along my axes, and they will help me plot my shape. Even if I don't remember, is this a cardioid or what type of limosome is this? Plotting with theta as those points will always work to give me my shape. A limosome with dimple will have the value of A larger than the value of B, will never go through the origin. We'll find out why in a minute. And here's the general shape. Cosine has symmetry along the x-axis, and y has symmetry, and sine has symmetry along the y. And these same points along the axes are great points to plot to try to figure out how this looks. The limosome with an inner loop, B is going to be larger than A in this case. The inner loop will always go through the origin. Cosine will have symmetry along the x-axis again, which is true for this one. And those same points are helpful. Now, all of these can be plotted on the graphing calculator. I'm going to show you how. And then we're also going to do some of these by hand using a table of values with all of these angles that are right along the axes. So here's how you would graph it on a TI-84 plus CE. First thing is you want to make sure that you go to your menu and choose radians. That's huge. You also want to make sure that instead of choosing functions that you choose polar right underneath that. Both of those have to be changed to graph a polar function. If you then select the y equals button, you'll notice that because you pick polar, it no longer says y equals, it says r equals. And when you type it and you type the variable button instead of typing x, it will show up as theta. And then we can graph it. We can change the windows as needed. Let me kind of show you how that would look a little bit. Let me just get this so you could see it. So if I wanted to graph in polar, I go to mode. I want to make sure radians is highlighted. It might already be. I'm going to change functions to polars and hit enter to select that, and then I'll quit that. I'm not going to go to y equals, but notice these now say r equals. So let's say I want to do a cardioid. A cardioid would have the same values for A and B. Maybe I want one to have symmetry around the y-axis. I'll pick sine. And then when I pick my variable button, it'll pick theta. I'm going to graph this. Now, I'm not seeing very much. That's because of my window. So let me change my window here. so that I can figure out kind of how I want this to look on this, because I'm not seeing enough on this. So this is my theta value from 0 to 2 pi. That's fine. But x, I plugged in numbers like 5 and 5. That will go up to 10. So maybe I'll go negative 10 to 10. I'll do a scale of 1. Same thing on the y. I'll do negative 10 to 10. When you're doing polars, your x's and y's will need to be the same because you're going to have this like circular shape. Now, why does this look so funny? If you look, do you see how the x-axis is spaced out wider than the y-axis? So it looks funny. The symmetry is a little bit off on this graph. It's shaped as a rectangle and not as a square, so it's kind of got a slightly funky window. The way I could change that is by maybe adjusting my window, making the x's have more than the y's, like maybe going, I don't know, maybe negative 15 to 15. That might make it look more square. That's closer. That's closer. So that ratio is just off a little bit since it's shaped as a rectangle, but this is more about how it would look. But what if you're not allowed to use a graphing calculator? In fact, I'll just tell you now, when you guys take your test, you will not be using a graphing calculator and you will not be using Desmos. So we'll provide some tables for you that will be, I think, quite helpful. Let's take a look at this first one. If I wanted to graph this. Now, first of all, this is not a circle because a circle would be 4 times sine theta. It's not a rose curve because a rose curve would have a multiplier with theta. So this is one of my types of limacons. I don't think it's a cardioid because I don't have the same number for both A and B. So I don't think it's a cardioid. But what I'm going to do is I'm just going to plug in numbers along the axes. I'll plug in a 0. The sine of 0 is 0. Plus 4 is still 4. So along the 0 radian angle, I will move out 4 units. At pi over 2, sine of pi over 2 is 1. 4 plus 1 is 5. At pi, sine is 0 again, so this would be 4 plus 0. And at 3 pi over 2, sine is negative 1. 4 minus 1 is 3. So if I connect these, what I end up with, notice how it does not go through the origin. This will be a limaçon with dimple that I'm having a very hard time drawing. And what that dimple looks like, that dimple is just a little indentation here. I often exaggerate how that really looks. It's just this little, it's so sad. That is such a sad little graph. I'll try it one more time. Let's see if I can do a little bit better. A little bit better. Okay, it's not quite circular. Notice how the numbers are not quite the same. There's this little dimple or flattening out part kind of right in here. All right, 1 plus cosine theta. This is 1 plus 1 cosine theta. This should be a cardioid because A and B are the same. But if I plug in a 0, cosine of 0 is 1. Plus 1 more is 2. At pi over 2, cosine of pi over 2 is 0. So this is 1 plus 0. At pi, cosine of pi is negative 1. I get 1 minus 1. This is why a cardioid goes to the origin. There is a spot where the zero's out. And then at 3 pi over 2, cosine zero's out again. I have 1 plus 0. So let's see, this goes here and here. So as I draw this, I'm going to make this shaped kind of like a heart. Now, this is not a point down here. This is a curve. It's kind of flattens out. This can be tricky to draw. You just want to make sure it goes wider than you think after you get past kind of the heart part. So this part, and then go wide before you kind of widen out there. All right, the last one, you could probably guess this is probably a limacon with an inner loop. Notice how the B value is bigger than A. But if I plug in a 0, the sine of 0 is 0. 3 times 0, this part is still 0. 1 minus 0 is 1. At pi over 2, sine is 1. So this would be 1 minus 3 times 1, or negative 2. At pi, sine is 0 again. 1 minus 0. 3 pi over 2, y is negative 1. This is 1 plus 3 because I had negative 3 times negative 1, which is 4. All right, so what happens here? So in the direction of 0, I'll go 1 unit. In the direction of pi over 2, I am going -2 units, means backwards. This is going to form the inner loop. When you go into the negative, this forms the inner loop. At pi, I'll go 1. And at 3 pi over 2, I will go 4. 1, 2, 3, 4. Now, here's how this always works. The inner loop always connects to the origin. And then you can kind of form similar to a cardioid from there. Just try to shape this out a little bit better. That kind of works. And that's how you do that one. And this is a little bit longer set of notes, but that is the end of notes for 6.4.